Hi everyone, and welcome to the video for the very last lab for NEL 270, Lab 7 on DC power supplies. In this lab, we're going to investigate a particular DC power supply that we have in these boxes here, and we're going to investigate its properties and how it behaves. Along with this power supply, we also have these particular module cards, which we'll use during the lab. These are to provide connectivity through this power supply to other parts of the supply, and also to plug in different modules such as the bridge rectifier and the 7805 voltage regulator we will encounter later. So this linear power supply has 4 stages to it. First of all, we have incoming mains voltage coming into the power supply. We then put that through a transformer, and this is a center tapped transformer, so we have 2 outputs from that. This then goes through a bridge rectifier, which we will plug in later, this module here, and that rectifies the voltage. That rectified voltage then goes through a smoothing capacitor, and we have a selectable bank of capacitors here. So we can select between either no filtering, 1 microfarad of filtering, or 1000 microfarads of filtering. We then finally have our voltage regulator, which is this module here, which we can use to regulate the voltage, and we'll see what that does later on. That then connects to an external load here, and with this load we can switch between either 330 ohms or 470 ohms of load. The first thing we are going to do is look at the operation of this transformer. So the first question asks you to, with the transformer plugged in, measure how it behaves, measure its performance. We want to do this using our multimeter, and because we are putting an AC voltage into a transformer, we expect to get an AC voltage out as well. To do this measurement, we are going to be using this link card here, which provides just a straight pathway between 2 points. You can see the traces on the circuit board there showing the connectivity. So what we're going to do is we're going to plug this link card into our power supply module. We're going to get our multimeter and connect that across points C and G on this power supply module. Our multimeter connected, we're going to turn it to an AC voltage. These transformers are rated nominally for 6.3 volts AC. Some of them will have a slightly higher and working voltage, about 7.2 volts. It varies a little bit from module to module. If we now turn the mains power supply on, we can see that voltage reasonably quickly climbs up to 6.52 volts AC. So across winding 1, we have 6.52 volts, and that is the unloaded voltage. That is, there is no load, there's no resistance connected to this output. What we can then do is connect in a load using some banana to banana wires and measure how well this performs with a load in place. So following the diagram shown on page 4, and jump this across so the positive supply goes to our load. And we can see that the output voltage drops slightly. Currently, we are set onto a 330 ohm load. You see it takes a moment to stabilize. And then now we read 6.48 volts AC out. So we can see that we've had a slight decrease in voltage due to the application of this load. If I remove that load, it returns back to our 6.52 volts AC. So those are our measurements for the first winding, secondary winding 1. If I turn the power off, we can repeat this for the other secondary winding. So I remove the link card from the power supply module and I plug it down the bottom. This is a center tapped transformer. You can see that denoted here. So this center rail is effectively our ground reference. These 2 ends either here are our 2 output voltages. So I plug that card in and I move my multimeter across to now probe the other output of the secondary. I turn the power supply on, voltage climbs up to 6.52 volts AC. And again, I can connect a 330 ohm load on the output of that secondary, and I get a output voltage of 6.48 volts AC. So again, we see a slight reduction in voltage due to that loading. So that is our data for table 6.1. If you can fill in here. There are then a couple of questions. One about whether these voltage values we measured are what we expect, and if not, why they're not what we expect. For this, you should consider things like the rating of the power supply, or the rated output voltages, and whether the effects you observe with and without loading make sense. The other thing we can do, I remove the multimeter to clear this up a little bit, turn the power off, is we can have a look at what is going on with the oscilloscope. So what we're going to do is we're going to measure the voltage waveform on one of these loaded secondary coils using the oscilloscope. What I'm going to do that is I'm going to leave this on the secondary winding, the secondary winding. I'm going to hook the oscilloscope across this link card where there are some probe points. We also want our load connected, so I'm going to reconnect in our 330 ohm load. So now we have 330 ohms on the output of this and our oscilloscope probe attached to probe the circuit. To help with this measurement, I'm going to make sure this probe oscilloscope is set up properly. Currently, I have it set on 10 times this channel and 10 times on the probe, so that should measure everything accurately. I turn the power supply on, and I'm going to scale what we're seeing on the oscilloscope. And this is the waveform we get. And we can see it's not an exact sinusoid, it's a bit of a clipped sinusoidal waveform. And so there's a question now asking whether this is what we expect to see, and if not, why it might not be what we expect. I suggest you have to think about what you expect mains voltage waveforms to look like, compare it to what we've got here, and then think about why that might be different. And when you do that, consider things like what else is connected to the same power supply in this room in general, in this lab, in this wing, etc. There are many other devices operating on this voltage as well, which may have an effect. So I suggest you consider those. So that is our transformer. The next thing we're going to look at is this bridge rectifier. Here we have a full wave rectifier on this module here. And you can see the 4 diodes connected as a full bridge rectifier. What we are going to do is place that across one of the secondary windings, plug them there. And we're going to make sure that we have our 330 ohm load connected as well. Currently, I want the filter capacitor switched out, so I have this filter setting set to out. We're then going to measure the load resistor's average DC voltage using our multimeter. So we take our multimeter and put that across our load, push that to a DC voltage, scale that as need be, and turn power supply on, rescale, and we see we are getting 4.5, about 4.52 volts across our load. There's some slight variation there. So between 4.5 and 4.53 volts. That is the average DC voltage across our load. However, this doesn't really tell us the full story of what's actually happening. What we can do is measure this more accurately using the oscilloscope. So if I disconnect the multimeter to keep the circuit nice and tidy, still leaves the 330 ohm load connected and the filter capacitor set to out, so it's not connected at all. We can now measure the voltage across this load. So again, the load connected, what I'm going to do is I'm going to use this link card here to give myself some easy probing points. I'm going to probe the voltage across the load. Then I turn that power supply output back on and rescale the oscilloscope. And we can see the waveform we are getting out. Notice that the ground of this waveform is down the bottom here. So now we actually have a DC voltage out rather than an AC voltage. We have a single-sided voltage, but it still has this variation on top of it. If we measure the peak-to-peak voltage on the signal, we find there is 8 volts peak to peak. So that differs from what we may have expected from our DC reading on the multimeter. Remember, that was taking an average reading. This is, in fact, still has a variation of 8 volts peak to peak. And this is the behavior of our rectifier. It takes that AC waveform and converts it into a DC waveform like this. However, it also leaves this ripple on here. Effectively, we're still going up and down like that. What you want in a pure DC output is a nice flat DC voltage. What we can do to help improve this is add in some capacitance to smooth this waveform. Now we're going to look at the operation of the smoothing capacitance in this circuit and how it can improve our DC voltage output. What we're going to do is modify our circuit now so that we have our transformer, our full bridge rectifier. We're going to add in 1000 microfarads of capacitance on the output of this bridge rectifier, and we're going to retain our 330 ohm load. So what I can do on our power supply module, I have the bridge rectifier still installed. I can switch this filter to 1000 microfarads. We then want to measure the DC voltage across our load. Again, we can do that using the multimeter. So if I connect our load into our circuit, then using our multimeter, we can measure the output DC voltage. We probe across the load. Set this to a DC voltage and turn our supply on. And we can see, compared to the last section, our DC voltage has increased. So we now have an average DC voltage of 7.36 volts. So it's a significant increase from before. That is telling us that our smoothing capacitor is having an effect. Remember before, we had 4.52, 4.51 volts. Now we have 7.36 volts. And again, we can investigate what's going on here a bit further by using the oscilloscope. So if I remove these connections and remove the multimeter for a moment, then again, use the link card to connect across so I have something I can probe off of. I then connect the oscilloscope probe across the load as required and turn the output on. Before, remember, we had this rectified waveform. With that capacitance in place, we now have a much smoother waveform. So there's a question here asking whether this is what you expect and why or why not. So you want to discuss whether this result is what you expected to see. We can also have a bit more of analysis of the signal. We can blow this up on the oscilloscope a little bit. We can see that while it's a bit jittery, we can see there's a bit of a triangular waveform there. We can fix this jitteriness by changing the triggering of this oscilloscope. Currently, this is trying to track the line voltage, that is the voltage coming from the mains, which runs at about 50 hertz. However, there is some slight variation on that. That frequency does vary over time. So this oscilloscope doesn't necessarily have that ability to track it that well. What we can do is change our source to be what's called the line voltage. And this then, because the oscilloscope is connected to the same mains voltage, it can then track those slight variations in that frequency and make this waveform a bit more stable. So now we can measure the peak-to-peak voltage on this waveform, which is our voltage ripple. Remember, for a perfect DC voltage, we want a flat, constant voltage with as little ripple as possible. Currently, on this signal, we are measuring 200 millivolts peak to peak. So we have 200 millivolts peak to peak of voltage ripple. You notice there's also a formula here to predict or to try and calculate what that ripple should be. Bear in mind, this is using the DC current. Remember, we know the average DC voltage. We measure that with the multimeter. We know the load resistance is 330 ohms, so we can calculate that current. We know the capacitance we have in place. This frequency is the mains frequency, which is 50 hertz. Note that if I try and read the frequency off the oscilloscope, I read a frequency of 100 hertz. And that's due to this full bridge rectifier. Every half cycle is being rectified to a DC voltage, so I get 2 half cycles DC per 1 cycle AC. So the frequency appears to be doubled. For this formula, we want to use that 50 hertz, and that doubling is already accounted for in this formula. So you should be able to calculate what that peak-to-peak voltage ripple should be and compare that to the measurement of 200 millivolts peak-to-peak that we have on the oscilloscope. What we can also do is we can take an external capacitor, such as this 470 microfarad capacitor, and we can connect this across the output to see what happens to our ripple voltage. So here we're told to connect across sockets C and G. These two here. So on the outside of this, after the bridge rectifier and after our built-in smoother capacitance, we're going to add some more capacitance in parallel. To do that, I'm going to touch them across the leads of this link card. And they're back on. Put a capacitor in parallel. We can see that our waveform changes, and in fact, our ripple decreases. So without the capacitor, and then with the capacitor. With the capacitor, our ripple has decreased to 140 millivolts peak to peak. So from 200 millivolts peak to peak down to 140 millivolts peak to peak. So that's the behavior we observe. There is a question here about asking about what happens to that ripple voltage and why it happens. So think of what the effect of adding this capacitance in parallel is having on this circuit. Okay. The next thing we are going to look at is the behavior of a voltage regulator. For that, we have the voltage regulator on this card here. This is the 7805 voltage regulator, which is a reasonably standard, nothing too fancy, but pretty reliable workhorse of a voltage regulator. The data sheet for this series of regulators is on page 13 of this lab. So there's all the information you want to know about it there. A note here is that this series of regulators are produced by Texas Instruments. It's the 78 series. 7800 indicates the 78 being a non-inverting voltage regulator with a fixed output. The last 2 digits indicate the voltage. This is a 7805. So this is a 5-volt output regulator. So what we're going to do is figure out first of all, how this regulator behaves by itself. If you look on the data sheet, you'll notice there is a dropout voltage specified for this regulator, specified down here. And we can see that has a typical value for the ones we're using. We're using the MC7805. This is a typical value of 2 volts DC. The idea of this is that the input for this fixed voltage regulator needs to be larger than the output because this regulator consumes some voltage in its operation. That minimum difference between the input and output voltage is what we call the dropout voltage. So if this has a dropout voltage of 2 volts, we then know that we need, for an output voltage of 5 volts, a minimum input voltage of 7 volts. So that 5 volts plus our dropout. What we're now going to do is connect this regulator into our linear power supply module, making sure these terminals are correctly oriented. If it's backwards, it's not going to work. So we can plug this into our power supply. We can also use our DC power supply here to just provide some easy DC power to the circuit to allow us to do some easy testing and analysis. What we're going to do is connect the positive terminal of our power supply in as an input to the voltage regulator, our ground to the other side. So we end up plugged in like so. This is coming from our DC power supply over here, and this is our voltage regulator. Note that currently the transformer and the main rectification is disconnected. We'll come back to that in a minute. We currently have the power supply set to 15 volts DC, and we are set to 330 ohm load at the moment. We want to now select the 470 ohm load. We also want to change our filter capacitance to 1 microfarad. So I can change those on the linear power supply module. I can then turn the power supply on and measure the voltage across the 470 ohm load. If I do so, I measure an output voltage of 4.96 volts. So this regulator is supposedly going to go as 5 volts. We've got 4.96 volts. We can compare that to what is specified on the data sheet. You'll notice there is an output voltage range specified for our module, the MC7805C. This is specified as being typically 5 volts, but anywhere between 4.75 and 5.25 volts. So using that information, you should be able to determine whether what we measured, that 4.96 volts, is within that range and therefore within the specification of the data sheet. Now what we want to do is start to decrease the input voltage, that 15 volts, and wait until the output voltage drops below 4.8 volts. I can connect a couple of crocodile clip leads across the output load. Currently of our 4.96 volts. I can start decreasing the input voltage. Currently it's set to 15 volts. As I start turning that down, I can keep an eye on what happens to my voltage out of my regulator. So coming down to 10 volts, 8, 7, 6 volts. And we want to stop when we get to below 4.8 volts. I've gone a little below then, so I'm going to increase the voltage slightly. And we see that the output voltage drops to about 4.8 volts. When the input voltage is 6.2 volts. So we have an input voltage of 6.2 volts and an output voltage of 4.8 volts. So based upon that, we can figure out what the actual dropout voltage of this regulator is and compare that to what is shown on the data sheet. And we can compare that to the range of values specified by the manufacturer. One thing to note is that manufacturers are sometimes a little pessimistic with what they state on the data sheets to ensure that the product they're selling will be within the range they specify, so people get what they expect. Okay, so that is the behavior of our voltage regulator by itself. Now what we are going to do is measure what's called the ripple rejection of this voltage regulator. So remember that we have coming from our transformer some AC waveform. We put through a rectifier that turns it into a full wave made of 2 cycles. We put through some smoothing capacitance. We get a smoother DC voltage out, but it still has some ripple on it. What we want for an ideal DC output voltage is a perfectly flat, in this case 5 volts, so there's no ripple on it. And a voltage regulator such as the 7805 offers a certain amount of what is called ripple rejection. You know, on the data sheet that is listed as being typically 83 decibels of ripple rejection, but at least 62 decibels. What we are going to do is we are going to actually measure this amount of ripple rejection. So what we're going to do is use this power supply and the 6.3 volts AC from the transformer to provide some artificial ripple, and we're going to supply 20 volts DC. If there was no ripple, this 20 volts DC will be converted nicely to a 5 volt DC output. We're going to add some ripple in using a transformer to try and corrupt that signal, add more ripple, and so we get a better measurement of the properties of this regulator. So I am going to set the load to 330 ohms and the filter capacitance to 1 microfarad. So very little capacitance and a small load. I've currently got the 20 power supply connected up to supply 20 volts DC into our circuit, and our transformer set up to supply some ripple across to that as well. If I now go and turn the power supply on and rescale the oscilloscope, and if I probe the input ripple, we can see there is a reasonable amount of ripple on the input. So we have our waveform offset by the power supply voltage of 20 volts. But we have currently 17.5 volts peak to peak of ripple. So that is this input ripple voltage we want to record here. What we then want to do is also record the output voltage ripple. That is the ripple across the output of a regulator, so across the load. If I connect our oscilloscope probe across that, you can see we get a reasonably weird looking waveform compared to our input where we just had that peak to peak ripple. So if I connect this across the output, I can see there's not a lot to see with the power supply on, so remember to supply 20 volts. What we can do is start scaling this up to try and see what's going on. The problem we'll run into on this oscilloscope is that we're trying to show a quite small AC waveform against a relatively quite large DC voltage. And so we'll quickly hit a display limit on the oscilloscope where it can't actually show us what's going on. What I'd like to do to rectify this, get around this, is first of all have the oscilloscope probe set to 1 times rather than 10 times. That gives a bit more precision. I've also set the oscilloscope to be on 1 time as well. And I can change what's called the coupling of this channel. So I go to channel 1, current's in DC coupling, that basically means measure everything. I can change it to AC coupling, which says basically ignore all the DC component, just show me the AC component. If I bring that back on screen, I can now dial that up. And I can see the AC component, which is our ripple voltage. And we can see it's kind of all over the place and a bit nasty. I'll fix the triggering by setting that triggering back to a line trigger. We can still see that's quite noisy though. What I can do to clean this up a little bit is I can go to the acquisition settings and turn some averaging on. On this oscilloscope, there is a button labeled acquire. I press that. It takes me to the acquisition menu. Currently, we are set to normal acquisition mode, which is basically just sample what's there. I can change that to an averaging mode. There's also this high resolution mode, which does a similar but slightly different thing. If I put on the averaging mode, and I kind of 8 samples for averaging, I can now more accurately measure the peak to peak ripple. Our output peak to peak ripple is 2.58 millivolts. So 2.58 millivolts of output ripple. Again, compared to our input ripple, try to rescale that, we can see it's significantly larger. Remember, that was our 18.7 volts peak to peak. So 18.7 volts peak to peak of input ripple, and our 2.5-ish, rescale it up again. And our sitting down a little bit. And 2.5, 2.6, let's say 2.6 millivolts of peak to peak ripple on the output. The ratio between those two, the input ripple and the output ripple, gives us the ripple rejection of our regulator. Remember, on the data sheet, it is specified in decibels, so we want to calculate that ripple rejection ratio in decibels as well. The ripple rejection is the ratio of output to input. We usually flip that around to get a bigger number. So the input ripple divided by the output ripple. We can then compare that to the value stated in the data sheet to see if that matches up with what the manufacturer states. So we've now looked at the behavior of a linear power supply module. Now we've measured the four main parts of this: the transformer, the rectifier, the filtering capacitance, and the output regulator. In practice, we have all these four parts in for a single linear power supply module. When we are using this in practice, we're looking to convert energy from AC mains voltage to a constant DC voltage. There's a couple of questions here. One is asking you to consider the waveforms that we saw from each of these stages, and therefore, based on that, to discuss how each part, how each stage contributes to the overall functioning of a linear power supply module. That is, what is the purpose of each part? What does each part do? Considering our four parts: our transformer, our rectifier, our filter, and our regulator. Lastly, there are a question asking for you to suggest two or more situations where a linear power supply would not be a suitable choice. In answering that question, I suggest you consider things like what alternative power supplies exist. This is a linear power supply. Are there other types of power supplies? If there are, what advantages do they have? What are the differences between them and a linear power supply? And also, considering this linear power supply, what are some of the limitations of these kinds of things? Again, you can look it up. You can also consider just looking at this linear power supply. Perhaps you can spot a couple of things as well that limit its use. That is the end of the lab. Thank you everyone